We already looked at left and right Riemann sums. We're going to look at midpoint and also using trapezoid to estimate the area underneath the curve. So we have our left sum uses the left height of the rectangle, our right sum uses the right height of the rectangle. And now what we're going to do is actually use the midpoint between our two x values, so the midpoint of delta x, to get the output of our rectangle. So what we're going to be doing is using the midpoint here to find our height. Okay, so let's go ahead and actually what we know is that using the midpoint is a more accurate Riemann sum, because when I use the midpoint, some of the curve is above the curve, and then there's a little bit of the curve that is not accounted for. So it kind of averages itself out a little bit better. Okay, so we're going to do the midpoint sum. So midpoint sum of the curve y is equal to x squared on the interval 0 to 2, and we're going to do even subintervals. So again, to get even subintervals, we do delta x is going to equal b minus a, so 2 minus 0 over 4, the number of intervals, and I get it's going to be 1/2. So over here, I'm just going to sketch in my rectangles just so we can see what it looks like. I have 1/2, 1, 3/2, 2. And we now have to find the midpoint of each one of these rectangles on the x-axis. So between 0 and 1/2, the midpoint would be 1/4. So I'm going to build my table. I need the height at 1/4. I need the height at 3/4. And then between 1 and 1/2 would be 5/4. And between 1.5 and 2, halfway between 1.5 and 2, would be 7/4. Okay, so there we go. So we're using the heights of each one of these um, outputs. So I'm going to go ahead and draw in my little rectangles here at the midpoint, using the midpoint as the height. Okay, and we can see that part of the curve is being over, the rectangle is a little bit over the curve, but it also is missing some of the curve as well. So again, it kind of evens itself out a little bit more, so it is a better estimate. So we go ahead and we say that the area is about equal to delta x, and in this case, it would be f of 1/4 plus delta x times f of 3/4 plus delta x times f of 5/4 plus delta x times f of 7/4. And I personally like to take out the delta x if I can. So we're going to do delta x times f of 1/4 plus the output of 3/4 plus the output at 5/4 plus the output of 7/4. Okay, so I get area is about equal to, oh, I didn't get the outputs. For x squared plus 1, I got 17 over 16, 25 over 16, 41 over 16, and 65 over 16. So I'm going to go ahead and plug those in. I have delta x of 1/2 times 17 over 16 plus 25 over 16 plus 41 over 16 plus 65 over 16. And all said and done, when I simplify that, I get 4.625. So the area is about equal to 4.625. Remember, a Riemann sum is a estimation of the area underneath the curve. All right, or the estimation of the integral. All right, next up, use the midpoint sum with 3 equal partitions. And this time we're given a table. So to estimate the area underneath the curve, we have our A is 1 and our B is 7, and I have our N is 3. So I'm going to use delta X is equal to 7 minus 1 over 3, which gives me an equal partition delta X of 2. Okay, so every 2 units, I need another rectangle. So I'm going to build my rectangles like that. I see that 2 is the midpoint between 3, 4 is the midpoint between 3 and 5, and 6 is the midpoint between 7 and 5. So I go ahead and find my area. My area is about equal to, and I'll just write out the formula, delta X times f of 2 plus f of 4 plus f of 6, since these are the heights, okay? And then lastly, we substitute in. The width is 2, and then the output is f of 2 is 5, plus f of 4 is 8, plus f of 6 is 19. I get area is about equal to 64. All right. Now an even more better method, more accurate estimate of the area under the curve is what I really mean, is using trapezoids to estimate the area. Okay, so remember trapezoids, the area of a trapezoid is 1/2 times base 1 plus base 2. So you're averaging the two bases and then multiplying by the height. When I look at this so it should look like this, base 1 plus base 2 times the height. Now, when I look at this, I think, okay, the height in this case is delta X, and our base 1 and base 2 are actually our two different heights. It's f of x1 and f of x2, and so on and so forth. So our height, we're calling our bases, they're actually our heights, okay? And our height is actually our base. So let's go ahead and I'll just say that the area of a trapezoid is equal to delta X times f of x 1 plus f of x2 all over 2. Okay. And then we're going to use the sum of that over and over and over again. Fun times. Okay, so we're going to use the same curve as we had before, but we're going to use trapezoids to solve. So I am going to build a trapezoid for equal partitions. So 2 minus 0 over 4. Wow. Okay. 2 minus 0 over 4 is 1/4. So that's going to give us our delta x. 1/2, sorry. So I have 1/2, 1, 3/2, and 2. So one, yeah. Okay. So we need to use both heights of the rectangle to make a trapezoid. Okay, so we're going to use the left hand height and the right hand height to make a trapezoid, not a rectangle. Okay, so I get something like this. I'm going to have height 1 times delta x plus this is height 2, and then we get a little diagonal line. Okay, so we're going to have we're going to build a bunch of these trapezoids right here. And to organize myself, I always write a table. So I need my heights at 0, 0 0.5, 1, 1.5, and 2. So this time, because we're using a trapezoid, we need both the both side, all heights, all 5 heights in my 4 subintervals. So f of 0 is 1, and then we have 1.25, 2, 3.25, and 5. I just did those in the calculator. And now we're going to add up, get the sum of all of our trapezoid areas. All right, so I have area is about equal to, and I'm going to write this out the long way first. Okay, area is about equal to delta x times, we're going to do f of 0 plus f of 1 over 2 plus delta x times f of 1 plus f of 2 over 2. So I have f of 1 plus f of 2 over 2. Now I'm going to take f of 2 plus f of 3. So plus delta x times f of 2 plus f of 3 over 2. And then one more, we're going to take f of 3 plus f of 4. So delta x, I'm going to run out of room. I put it underneath. Okay, plus delta x times f of 3 plus f of 4 over 2. I see that I can GCF out my delta x's and the over 2's. Every single one of the terms has delta x over 2, so I am going to bring it out to the front. Delta x over 2. And then I notice that every single height is being added twice except for the beginning height and the ending height. Check it. I have f of 1 plus f of 1, f of 2 plus f of 2, f of 3 plus f of 3, and I just have these ending heights that didn't get added twice. So I'm going to write this as f of 0 plus 2 times f of 1 plus 2 times f of 2 plus 2 times f of 3. So every height on the inside of our trapezoid, of our curve here, gets added twice. And then I only have one of the endpoint. Okay, time to plug in. So area is about equal to delta x is 1/2 times 1/2 for the divide by 2. And f of 0 is 1 plus 2 times f of 2, 1.25, plus 2 times 2, plus 2 times 3.25, plus 5. So area under the curve is about equal to 4.75. And when I compare that to my midpoint area of 4.625, it's pretty stinking close. We know that the trapezoidal Riemann sum is the most accurate estimation that we have. Okay, it's the most accurate. Okay, last one. This is we're going to find the acceleration of the particle. So we need, the acceleration of the particle is given. If the initial velocity of the particle is v of 0 is equal to 3, we're going to find the velocity at time is equal to 8. So you don't know this, but what we need to do is, we know that velocity is the integral of acceleration. So I'm going to take the integral of acceleration. So I need to find which is the area underneath the curve. Okay, so I'm going to find the area underneath the curve, or the area of A of t. And when I do that, I get the velocity of t, but I also, remember, have to add my constant of integration. Okay, Okay, so we're going to find the area under the curve. We're going to split this up into trapezoids like so. Notice the delta x's are not the same, so I see that the delta x here is 2, the delta x is 3, the change in x is 2, and the change in x is 1. So we're going to take the velocity of 8 is equal to the area under the curve, which is delta x times a of 0 plus a of 2 over 2 plus delta x times a of 2 plus a of 5 all over 2. Heights are being averaged times delta x times a of 5 plus a of 7 all over 2 plus delta x times a of 7 plus a of 8 all over 2. So it's the so what I get next, delta x would be 2 times, and I'm just going to substitute in my y value, so I get 0 plus 4 over 2 plus this time the width is 3 and a of 2 is 4 plus 13 over 2 plus 2 times 13 plus 21 over 2 plus the change in x is 1 times 21 plus 23 over 2, all plus c. Ooh, I forgot my plus c here. Plus c. Okay. So, because the curve can be shifted up or down, is basically what we're saying. Okay. So v of 8 is equal to, when I multiply this all out, I get 85.5 plus c. And then I know from the initial statement that my initial value, the point at 0, 3 of my initial velocity is 3, because at time 0 it says the velocity is 3. So this is my c value because it's the y-intercept. So I get v of 8 is equal to 85.5 plus 3. So the velocity at 8 is 88.5. And I don't think there's any units, so we're just going to leave it. All right, so that is that for today.